In this video, we're going to solve some augmented systems with inverses, and then we're going to prove some properties of inverses. So first we have a theorem, we're going to prove it, and then we'll do a computational example with it. So if A is invertible, then for all vectors B and R, AX equals B has the unique solution x is equal to A inverse B. So essentially here, instead of solving for x by doing some row reduction, we can just use the inverse and multiply it by the vector and get our solution to x. So we need to prove it exists. So we're going to assume that A is invertible, and we're going to assume that AX is equal to B. Okay, so we have that AX is equal to B and A is invertible. This means it has an inverse, so we can left multiply by it. So now we have that A inverse times AX is equal to A inverse times B. Okay, now using the commutative property, we can group these up separately. So instead of A inverse times AX, we can use the associative rule to have this as A inverse times A. So we know this is just the identity matrix times X, and this is going to be equal to A inverse times B. And of course, the identity matrix times X is just X. So as a result, we have that X is equal to A inverse B. So we know it exists, but is it unique? So let's check. What we do is we're going to assume that AU is equal to B and U is equal to A inverse B. So this is the only solution for U. I'm going to show that. Okay, so we're going to plug A inverse B into U. So now we have A times A inverse B, and this is going to equal A times A inverse B using the associative property, which is just the identity matrix, times B, which is just B. Therefore, it is unique. Okay, so it exists and it's unique. So if we have AX equals B, we can solve X by taking A inverse B. So let's do that in this next problem. So we have the augmented A, which means that if we take a look at this, this is the matrix A with the column vector B. So first we need to find A inverse. So A inverse, if we remember, I'll write out the formula again. This is 1 over AD minus BC. And if we take a look at the original matrix A, which is A, B, C, D, our inverse is going to have the matrix D, negative B, negative C, A. Check out the last video if you want a refresher on this formula. So let's plug in some numbers here. 1 over AD minus BC. So A times D is negative 40. That's 8 times negative 5. And BC is 5 times negative 7, which is negative 35. So here we have negative 40 minus negative 35. So I'm just going to add this up quickly. So this is going to equal negative 40 plus 35, which is just negative 5. So this is going to be negative 1/5. I'll put the negative at the bottom. And our D, so our original matrix was A, B, C, D. So negative 5 is going to appear as the first entry. Our B is going to flip, so 5 becomes negative 5. Negative 7 will become 7. And of course, for our last entry is going to be the original A, so this becomes 8. Okay, so now we just multiply these together, and we're going to get 1, 1, negative 7/5, and negative 8/5. Okay, so we want to find X. So we want to find our solution here. So we know that X is equal to A inverse times B. So let's just put that in. So we have our A inverse, which is 1, 1, 7 over 5, and 8 over 5, and our B is negative 9, 11. So we can just do some matrix vector multiplication. So we have negative 9 times the first column, so this will be negative 9, negative 63 over 5, Then we're going to add 11 times the second column. So this will be 11 and 88 over 5. So here we have the result. Negative 9 plus 11 is 2, and negative 63 over 5 plus 88 over 5 is going to be positive 25 over 5, which is just 5. So here is our solution. And of course, you can always check that AX is equal to B. So if you take the original matrix A and you multiply it by this X vector 2, 5, you will get negative 9, 11 back. And you can check that on your own. So now that we know how to use it, we should learn some extra properties of inverses. So, theorem 1. If A is invertible, then A inverse is also invertible, and the inverse of A inverse is just A. So, what do we know? We know that A times A inverse is the identity matrix, and A inverse times A is also the identity matrix. So now we want to find a matrix such that A inverse times C is equal to the identity, and C times A inverse is equal to the identity. But what is this C really? So in other notation, we could just say, look, this is the inverse of A inverse. So that's really what we want to find here. But we already know there's a solution for this, and there's only one solution for this. So this A times A inverse is equivalent to the second line here. So this inverse of A inverse must be A, because there's only one solution for this. All inverses are unique. And similarly, this bottom one here, which I just deleted, should be this A here. So because inverses are unique, and we already know that A is an inverse of A inverse, that means that the inverse of A inverse must be A. So A inverse is equal to A. So that's the first part. The second part says that if we have two matrices A and B, they're both the same size, they're both invertible, then that means that AB is invertible, and the inverse of AB is equal to B inverse A inverse. So we want to show that AB times AB inverse is equal to the identity matrix. So we're going to substitute in B inverse A inverse for AB inverse and show that we still get the same result. So that's what we'll do. So we're going to take AB, we're going to multiply by AB inverse, and we'll show that this equals the identity matrix. So this is the same thing as AB, and let's substitute in what we think our inverse is. So AB inverse is equal to B inverse A inverse. Okay, now let's use the associative property. So we're going to group our B and B inverse together. And we know that B times B inverse is just the identity matrix. And of course, the identity matrix times anything is just whatever that anything is. So we're left with A times A inverse. And we know that just equals the identity matrix. So this holds. AB inverse is equal to B inverse A inverse. Now, on your own, you should show that this also works for the other side as well. So we should show that B inverse A inverse times AB is equal to the identity matrix. So you should prove that. I won't, because it'll take a little bit of time, but this is pretty straightforward, follows the same steps, so please do that on your own. Finally, if A is invertible and the transpose of A is invertible, if A is invertible, then the transpose of A is invertible, and the inverse of the transpose is the transpose of the inverse. So we're going to prove this a little bit differently. So it's pretty hard to work with these transposes and inverses right off the bat. So we're going to start from the other direction. We're going to say, okay, we want to end up at the identity matrix, so let's start there. And a nice property of the identity matrix is that it's equal to its transpose. So the identity matrix is equal to the transpose of the identity matrix. And we also know the identity matrix is equal to A times A inverse. And of course, this is the transpose of that. Since we're not substituting the identity matrix transpose, we're just substituting in the identity matrix. So the identity matrix is equal to A times A inverse transpose. Now, if you remember our transpose laws, we can distribute it. So A times A inverse transpose is the same thing as A inverse transpose times A transpose. Okay, now here's the interesting thing here. This is the inverse of A transpose. So what this really means is that if we have A transpose, we're looking for A transpose inverse. So that means that these two properties, these two values are the same. So A inverse transpose is equal to A transpose inverse. Why? Because the inverse is always unique. And we've shown through these steps that if we start with the identity matrix and use inverses and then use our transpose laws, we end up with this A inverse transpose A transpose, which is equal to the identity matrix. Therefore, A transpose inverse is equal to A inverse transpose. So I know a lot of inverses and transposes. That's why sometimes symbols are better than words. So hopefully you caught all that. If you have any questions, please leave them in the comments below, and I'll answer them as quickly as I can.